coming from a planetesimal disk, that it's an object that was ejected from a planetesimal disk. As I said, the ejection is very common, and most of the material that you will eject will come from outside the snow line. So you will expect an icy composition in this case, although you could also have material being ejected from inside the snow line, but statistically speaking, you will expect more material from outside the snow line. It could also be coming from an exo-or cloud, where you unbound the material as the star evolves in its main sequence and it gets to the post-main sequence phase, it loses mass, and some of the material that is barely bound in these exo-or clouds get unbound, and some of that material will be free. I mean, this material will be loose free in the interstellar space and might become one of these interstellar interlopers. So that could be another potential origin. Or it could have, its origin could be more related to a white dwarf or a supernovae. For example, in a supernova again, you lose mass very suddenly, right? So that some of the material that is bound to the star suddenly gets unbound. So that's another way to lose, that you could potentially lose planetesimals. So here I'm going to tell you about these two origins. I'm going to explore if Oumuamua could be representative of a population of objects that have either a planetesimal disk origin or an exo-or cloud origin. So, could Oumuamua be ejected from a protoplanetary disk? So what I will do here is I estimate what is the contribution. I want to estimate what is the contribution from single stars and from white binaries, so that I treat them as single stars. What will be the contribution from the planetesimal disks that are surrounding these stars? What will be the contribution to the interstellar medium, and can we get enough material in there to account for the detection of Oumuamua? So here what I do is, of course, the contribution, this is calculated in terms of mass density. So the units is like grams per cubic parsec. And the contribution is going to depend, of course, on the number density of stars. So it's going to depend on the initial mass function, right? So it depends on the number of stars per stellar mass. And then I assume that a fraction of them are single stars, because I'm going to be looking at the stars that are single. And then I assume that each star contributes about 10 to the minus 4 stellar masses in solids. So generally the disks that surround these stars have about 1% of the mass of the star. So that's 1%. So that would be 10 to the minus 2. But then you have the 100 to 1 gas to dust ratio. So there is a 10 to the minus 2 because of we think the disk is about 1% of the stellar mass, and then it's another 10 to the minus 2 because we are only considering the solids. So this is where the 10 to the minus 4 is coming from. And then I'm going to assume that most of the material is ejected, because as I said, like in the solar system, only a very small fraction of the material was left behind in the current planetesimal disk, the asteroid belt and the Kuiper belt, but most of the material that was there originally was ejected. So I'm going to assume that most of the material is ejected, and I'm going to assume that it's only the stars with planets that can contribute. Right, because under this scenario, I need giant planets in order to create these dynamical instabilities to eject the material. So,
do you make an assumption about the size distribution?
And not yet. I'm going to do that assumption later. So this is in terms of mass, of total mass, right? So, and then you plug in the numbers, and this is what you get. Of course, you normalize to all these assumptions here, right? But this is what you get from the contribution of stars M type to K2 stars and K2 to A. And I don't go I don't consider intermediate mass stars more massive than A because we need giant planets, right? And those stars have trouble forming giant planets because by the time because the snow line moves quickly beyond the 10-15 AU region before the planets have time to form. So I stop here, right, at A type. Yes?
So you made the assumption that the entire disk is
I make the assumption that the entire disk is gone.
But what about the Oort cloud? There's a substantial masses there? Or
right, so I do that calculation later,
okay.
So you'll see. And then I do a similar calculation for the contribution from tight binaries, where the assumptions are a bit different. The assumption here is that you have the tight binary, you have a circumbinary disk, that in this case is like 10% of the mass of the binary, and then 10% of the material in these disks gets to the unstable region, and all that material is ejected quite efficiently. So if you plug in those assumptions here, you get this number here. And of course, this number in grams per cubic parsec doesn't really tell you much. So what I do is, what I really want to do is to compare what is the expectation in terms of what is, in terms of the mass density of material that will be out there, what is the expectation compared to what are we inferring from the detection of Oumuamua. And that's what we have to assume a size distribution, right? Because Oumuamua is one single object. You can assume, you can infer a number density if you make some assumptions about the detection volume, right? And then, but then in order to go from an object of a given size, we assume that is 80 meters, to a mass density, you need to assume a size distribution. And this is, and we have no idea about the size distribution, right? So what I'm going to do is based on solar system models, solar system coagulation model, based on observations of small bodies in the solar systems, and also based on simulations of accretion. I assume a wide range of size distributions. Is a broken power law where there is a Q1 and a Q2 indexes, and they can vary between 2 and 6. So this really, it is a wide range of size distributions that I am assuming, and the comparison basically is that no matter what size distribution I assume, even if it's a wide range of size distribution, no matter the size distribution that I assume, what I infer from the detection of Oumuamua is between 10 to the 29 to 10 to the 35 grams per cubic parsec, is much larger than what I can expect from the ejection of all this circumstellar material from this protoplanetary, from these circumstellar disks. So the conclusion is that we cannot account using planetesimal disks, we cannot account for the amount of material that is inferred from the detection of Oumuamua, if you assume that Oumuamua is representative of an isotropic population, right? And I do the same for the exo or cloud origin. Here, what I do is that I assume that all stars are surrounded by Oort clouds that have about 10 to the 12 objects scaled to the stellar mass. So in the solar system, we expect to have about 10 to the 12 objects, and this is coming from, this is inferred from the flux of long period comets. It's about 2-3 per year. So as you can see, 2-3 per year is a small number, so it's a small number of statistics, but the idea is that we have about 10 to the 12 objects. So I assume that all the stars are surrounded by similar Oort clouds, but scaled to the stellar mass. And I assume a similar extent of the exo Oort clouds, similar to ours, but scaled to the Hill radius of the star. And then there are some dynamical simulations by Dimitri Veras that look at what are the effects of the different forces that are acting upon these, loosely bound objects in the exo Oort clouds, like at different galactic centric distances. And at the galactic centric, at the distance of the solar system, about 8 kiloparsecs, these exo Oort clouds, what affects the dynamics of these exo Oort clouds is basically post-main sequence mass loss and stellar encounters. So the main processes, so basically the bodies that are orbiting, this is in periods, so this is really semi-major axis, so this will be like, so particles that are loosely bound that are orbiting the stars at these positions, right, at these galactocentric positions. orbits that the bodies that are orbiting beyond these boundaries are subject to become dynamically unstable. And basically, this means that the processes that are dominating the clearing of these XOR clouds are stellar encounters for the stars that are still on the main sequence. But then for the stars that are already in the post-main sequence, what dominates is the mass loss, right? For stars in this from 1 to 8 stellar masses. So what I do is calculate what is the contribution from stellar encounters for stars that are still on the main sequence. Yes?
Could you back up 2 slides?
Yes.
So,
This? Yes.
One,
This one, yes.
So you're saying the mass or size scales with no radius?
This is the size.
That's the size.
Yeah, this is the size.
Okay.
Is the inner, right, I'm scaling both the inner edge and the outer edge of the
mass scale
of the cloud.
stellar mass.
And the mass scales with the stellar mass. So what I do is I calculate what is the contribution from stellar encounters of the stars that are still on the main sequence. And the way that I do this, again, this is going to depend on the initial mass function, on what is the mass of the number density of stars per stellar mass, right? It's going to depend on how many stars are still in the main sequence. Then I'm going to assume that each star has 10 to the 12 objects, which is this number here, scaled to the stellar mass. What this does is basically this just converts to the number, this is just for the size distribution, right? So I want to have objects that are larger than Oumuamua, so I need to assume some size distribution. And these will be objects that are larger than 2 kilometers in size, but I want to have the number of objects that are larger than Oumuamua, that is like 100 meters. So basically, this is what this factor is.